Section 13.1, right triangle trigonometry. On the right hand side of the slide you see a figure which is a right triangle, and if you look at the right triangle, the sides are labeled with specific names. The hypotenuse of a right triangle is always the side that's opposite of the right angle. So here is the right angle in this right triangle. The hypotenuse is always the side opposite that right angle. The adjacent side and opposite side, those are relative to the acute angle to which you are referring. So for example, in this case we're referring to this acute angle theta. If this is the angle to which we are referring, the opposite side would be the side opposite this angle theta here. The adjacent side is the side that's adjacent to this angle here. Once again, the hypotenuse is always the side that's opposite the right angle. So this section talks about the 6 trigonometric functions, and these 6 trig functions are simply ratios of sides of a right triangle. They are ratios of the lengths of sides of a right triangle. So each of these 6 trig functions, sine, cosine, tan, cosecant, secant, cotan, these are all defined to be specific ratios of the lengths of sides of a right triangle. So for example, if I'm considering this angle theta, the sine of this angle, the sine of theta, is specifically the ratio the length of the opposite side divided by the length of the hypotenuse. And all 6 of these trigonometric functions have similar definitions. So here you can see what those definitions are. So I just said previously the sine of angle theta is the length of the opposite side divided by the hypotenuse. The cosine of angle theta is defined to be the length of the adjacent side divided by the hypotenuse. So if I go back to the previous slide, the cosine of this angle theta, the ratio, the cosine, is the length of the adjacent side divided by the length of the hypotenuse. Tangent is defined to be the length of the opposite side divided by the length of the adjacent side. And then you can also see that these last 3 trig functions, they are reciprocals of the first 3. So cosecant is reciprocal of sine, secant the reciprocal of cosine, cotan the reciprocal of tan. So that tells me, for example, if the cosine of the angle theta is a half, the secant must be 2 over 1. At the bottom you see the acronym that relates or defines sine, cosine, and tan. Sine is defined to be opposite over hypotenuse. Cosine is defined to be adjacent over hypotenuse. Tangent is defined to be opposite over adjacent. So for example, I'm given a right triangle and I'm asked to evaluate the 6 trigonometric functions of the angle x. So that means I need definitions for the sine of x, cosine x, tan x, cosecant x, secant x, and cotan x. And all I need to use is the definitions of those 6 trig functions, because they're all defined in terms of these side lengths, 12, 5, and 13. So, for example, the sine is defined to be opposite over hypotenuse. So I go to angle x, the opposite is 12, the hypotenuse is 13, so the sine of angle x is 12 over 13. The cosine is defined to be the length of the adjacent divided by the length of the hypotenuse. Angle x, adjacent side is 5, hypotenuse is 13, cosine of angle x is 5 over 13. The tangent of angle x is defined to be the side opposite, the length of the side opposite, divided by the length of the side adjacent. So from angle x, the length of the side opposite is 12, the length of the side adjacent is 5, tan is opposite over adjacent, 12 over 5. And then I can see the other 3 trig functions are simply reciprocals of the first 3. Sine and cosecant are reciprocals, so 12 over 13 for sine, 13 over 12 for cosecant. Similar relationship with cosine and secant, and tangent and cotangent. So you could pause this presentation and try this problem. Evaluate the 6 trigonometric functions of angle theta. You can see you have one missing side length, but for a right triangle there is a way to determine what this side length is. You can determine this side length, which in this case is the hypotenuse. And then once you have all 3 side lengths, you can define the 6 trig functions. Take a minute and try this one. Pause the presentation first. So here you can see that with this right triangle, I can use the Pythagorean theorem here to determine the length of the hypotenuse. 6 squared plus 8 squared is the unknown squared. And I determine that hypotenuse is 10. Once I know the 3 side lengths, then I can define all 6 trig functions. So for example, sine of angle theta is opposite over hypotenuse. Angle theta, opposite over hypotenuse. 6 over 10, which reduces to 3/5. Tangent of angle theta, tangent is opposite over adjacent. Opposite 6 over adjacent 8. 6 over 8 reduces to 3/4. Tan of angle theta is 3/4. Cosine of angle theta, adjacent over hypotenuse. Angle theta, adjacent side 8, hypotenuse 10. 8 over 10 reduces to 4/5. And then once again, secant and cosine, those are reciprocals of each other. 4/5, 5/4. Sine and cosecant have a similar relationship. Tangent and cotan have the same relationship. 3/4 for tan, 4/3 for cotan. 6 is the exact same type of problem. The only complication at all with number 6 is that one of the side lengths, in this case the hypotenuse, includes a radical. But it's the same process. I'll use the Pythagorean theorem to determine the length of this missing side. Once I have all 3 side lengths, I can define the 6 trig functions. Pythagorean theorem tells me that this missing side length, this leg, is 3. Now that I have all 3 side lengths, I can determine any trig function. For example, tangent is opposite over adjacent. So here's theta. Tangent is opposite 3 over adjacent 3. Tan is 3 over 3, or 1. Cosine is adjacent over hypotenuse. Theta, adjacent is 3, hypotenuse is 3 root 2. So cosine of theta will be 3 over 3 root 2. 3 over 3 root 2. 3 over 3, that reduces to simply 1. So I have 1 over root 2. And then I'm going to eliminate the radical from the denominator by rationalizing, and I get root 2 over 2. So you can see with these 3 side lengths, I can define all 6 trig function values. This is a table for angle theta for 3 distinct angles, 30, 45, and 60, and the specific trig function values for those angles. And the reason that this table is identified in this section is because these are special angles that occur frequently in trigonometry. Now, as opposed to memorizing this table, if I know the definitions of the trig function values, like for example, cosine is adjacent over hypotenuse, and I know the ratio of sides in a 30, 60, 90 triangle, a 45, 45, 90 triangle, and again, a 30, 60, 90 triangle, then I can actually create this chart myself. So for example, if I know that in a 30, 60, 90 triangle, the ratio of sides is 1, 2, square root of 3. So in other words, I look at this triangle, the shortest side, the shortest leg, is the side opposite the 30-degree angle. That has length 1 in this case. The hypotenuse, which is always the longest side, that's always twice the size of the short leg. So if the short leg is 1, the hypotenuse is 2. The longer leg is always the short leg times root 3. So if the short leg is 1 in this case, the longer leg, this one here, the one opposite 60 degrees, that's root 3. So these are ratios of sides. If this shorter leg were, say, 5, then the hypotenuse would be twice that, which is 10. And the long leg would be root 3 times that value, so 5 root 3, if that short leg had been 5. Similarly, in a 45, 45, 90, this is even easier. The legs are always the same. So if this leg is 1, this leg is also 1. And the hypotenuse is root 2 times either one of the legs. So if a leg is 1, the hypotenuse is 1 times root 2. If one of the legs was, say, 10, then the hypotenuse would be 10 root 2. These side lengths would be 10, 10, 10 root 2. These are ratios of sides. So we'll go through this example. I'm going to pick up this example in a second video. So this video is going to stop here and we'll continue in a second video.